Welcome to this deep dive. Today, we're tackling a really core statistical idea, the binomial distribution.
That's right.
You asked for a clearer picture, and well, we're aiming to give you a really practical sense of what it is and, how it actually works.
Absolutely. Think about situations where you're doing something over and over, and each time there are really only two possible results. Success, failure, pass, fail.
Right.
That's the basic playground for the binomial. But for it to strictly apply, there are a few key things, sort of non-negotiables, that have to be true.
Okay, so what are those? What conditions need to be met?
Well, first, like I said, only two outcomes per trial.
Yeah.
Binary. Second, you need a fixed number of trials. You can't just keep going indefinitely. You decide beforehand, we're doing this 10 times or 50 times, whatever it is.
Okay, so a set endpoint, not just ongoing trials. Got it. What else?
And this is crucial. The probability of success, let's call it P, has to be exactly the same for every single trial.
Okay. So if you're flipping a coin, it's always 50-50, assuming it's a fair coin.
Precisely. Or like testing parts off a line. If the machine has, say, a consistent 2% defect rate, that PT stays at 0.02 for each part tested.
Makes sense.
And lastly, the trials have to be independent. One outcome can't influence the next one.
Right. So pulling one defective item doesn't magically change the chance of the next item being defective.
Exactly. Unless, of course, there's some underlying process change we're not accounting for, which would violate the binomial setup.
Okay, consistent conditions, independence. So let's say we had those conditions. How do we calculate the probability of getting, say, exactly 3 successes in 10 trials?
Right, that's where the formula comes in. But conceptually, what you're doing is, well, you're figuring out all the different ways you could get those 3 successes within the 10 trials. It could be the first 3 or the last 3 or mixed up in the middle. The formula counts all those combinations.
Okay.
And then multiplies that by the probability of any one specific sequence occurring. It's kind of clever how it combines the how many ways with the chance of each way.
So the order, or rather the combination of where the successes fall, matters in the calculation, even if we only care about the total number at the end.
Exactly. Now, you also mentioned mean and variance. These are really useful descriptors.
Yeah. What do they tell us practically?
The mean is basically your expected average outcome. It's simple. Just multiply a number of trials n by the probability of success, Pn times P.
So back to the defects.
Yeah.
100 items, 2% defect rate.
Hmm?
We'd expect, on average, 2 defects, 100.02.
Exactly right. That's your expected value. Now, the variance, that tells you about the spread. How much are the actual results likely to bounce around that average of 2?
Okay.
A smaller variance means you'll likely get results very close to 2 most of the time. A larger variance means, well, more unpredictability. You might get 0 or 1 or maybe 4 or 5 more often.
Got it. Average outcome and the typical spread around it. Now, something I've heard is that sometimes, if you have enough trials, this binomial thing starts to look like a normal distribution, that classic bell curve.
Yes, that's a really useful approximation. It tends to work well when at n, the number of trials is large.
How large is large? Is there a rule of thumb?
A common guideline is when both the expected successes, n times p, and the expected failures, n times 1p, are both at least, say, 5 or more, often 10.
Okay.
When that holds, the shape of the binomial distribution gets pretty close to a normal curve, and using the normal distribution can make calculations, especially for ranges of outcomes, much easier than using the exact binomial formula, particularly with large n.
A handy shortcut for big data sets. Cool. Now let's clarify something. Binomial versus negative binomial. They sound related but different.
They are related, but they ask different questions. Binomial. You fix the number of trials and count the number of successes. The question is about the probability of getting k successes.
Okay.
Negative binomial. You fix the number of successes you want to achieve, and you count the number of trials n it takes to get there. The question is about the probability that it takes exactly n trials.
Okay. So binomial is how many successes in n trials. Negative binomial is how many trials to get k successes. That's a key difference.
Precisely. It flips the perspective.
So when would the standard binomial distribution not be the right tool? Where does it break down?
Well, fundamentally, if any of those core conditions we started with aren't met.
Like independence.
Yeah. If trials influence each other, think about sampling without replacement from a small population. Pulling one item changes the probabilities for the next. Or
if the probability P changes.
Exactly. If the chance of success isn't constant, maybe a machine wears down over time, increasing defect rates, or a basketball player getting hot, their success probability might genuinely change based on recent shots. Binomial assumes stability.
Right, that makes total sense.
Yeah.
Dynamic situations mess it up. How does changing that p-value, the success probability, affect the look, the shape of the distribution?
It has a big impact. If p is zero point 0.5, perfectly balanced like a fair coin, the distribution is symmetrical around the mean. But if p is low, say zero point 0.1, most outcomes will cluster near zero successes, and the distribution will be skewed to the right. If p is high, like zero point 0.9, it'll cluster near the maximum possible successes, skewed to the left.
So the balance point shifts depending on how likely success is. Makes sense visually. What about cumulative probability?
Ah, yes. Sometimes you don't care about exactly k successes. You care about k or fewer, or maybe at least k.
Right, like what's the chance of getting 3 or less defects?
Exactly. That's a cumulative probability. You're summing up the probabilities of 0, 1, 2, and 3 defects. It's super common in practice when you're looking at thresholds, like in quality control.
Yeah, let's talk about that. How is it used there? Seems like a perfect fit.
It really is. Imagine a factory making widgets. They can't test every single one, right? So they take a sample, say 20 widgets.
Okay.
They know their historical defect rate, maybe it's 1%, that's P. Using the binomial distribution, they can calculate the probability of finding, say, 2 or more defects in that sample of 20 if the process is still running correctly at 1%.
Ah, I see.
If they actually find 2 or more defects, and the calculation shows the probability should be really, really low under normal conditions,
Then it suggests something might be wrong with the process.
precisely. It's a flag. It doesn't prove it, but it gives them a statistical basis to say, hold on, the chance of seeing this many defects just by random luck is tiny. We should investigate. It helps decide when to take action.
That's a really clear, practical application. Assessing risk based on samples.
Mm-hmm.
Well, hopefully this deep dive has really helped clarify the binomial distribution for you. The core idea is understanding those conditions, fixed trials, two outcomes, constant probability independence.
Yeah, when those hold, it's a powerful tool for figuring out the likelihood of different numbers of successes.
Definitely. So think about where you might see these kinds of repeated, independent, binary events in your world. What kinds of questions could you ask now about that data? Thanks for diving deep with us today.
Yeah, consider how knowing these probabilities might shift your perspective on events that seem, well, just random.